Okay, this is a conservation of energy problem that involves the calculation of power. Here we're given a volcano that is spewing rocks, 450 kilogram rocks, and to a certain height. We're assuming that the volcano imparts 1 joule of internal energy per kilogram to the rocks, so 450 for each rock, 450 joules of energy for each rock, and that the air drag force measures an average of 1 newton. And so if the volcano spews 100 rocks of this size every minute, what is the volcano's power output? So we just basically have to find out how much energy is associated with each rock, and then we have a rate of 450 of those. Um, okay, because we're told, or rather, sorry, we have a rate of 100 of those per minute, so per 60 seconds. All right, so let's first of all find the energy of each rock. Okay, so the energy of the rock. This is the energy that's imparted to the rock from the volcano. Okay, well, we've got 1 joule of energy times the 450 kilograms. Okay, so that's just, so per rock we have 450 joules. Okay, and that would be because we have joules per kilogram. Okay, so so we can have, oh, here we go. I wrote it incorrectly. It should be here. Joules per kilogram, because that's the amount of energy per mass, and then multiplied by the mass of 450 kilograms. So then our units work out. We lose the kilograms. Okay. Okay, so that's some of the energy. Obviously, energy also goes, well, to the, initially the rock has kinetic energy because it's flying up out of the volcano, but we're not given that. Instead, we're given the height. Okay, so that's just going to be the mass of the rock. Okay, so 450 kilograms times gravity, 9.8 meters per second squared, and then times the height of 320 meters, right? That's how high each rock flies. Okay, and so right here, this just represents the potential energy term of mgh. Okay, and our last term is the friction term. Okay, and we're told here that the air drag force measures an average of 1 newton. Okay, so that is the force. Okay, so we have air drag, so 1 newton of force, but that doesn't have units of joules. We have to multiply by the distance, so 320 meters. Okay, and then we have newton meters, the units of energy, and what this represents right here is just the energy going, or the work, but also energy done by drag. Okay. Okay. Now it's not negative because this is all the energy that's imparted to the rock, right? Because we know that they make it to 320 meters, and so then there had to be energy being dissipated to drag that entire time. So then the initial energy that was given to the rocks, that's what this represents. So this is the initial energy imparted to each rock by the volcano. Okay, so then our next step to find power is going to be energy over time. So power is energy total over time, okay, because it has units of watts, so it's energy per time, joules per second. And energy total is going to be the energy for each rock. All right, so the energy for each rock times the number of rocks, okay, and it's the number of rocks per unit time, and the unit time that we have here is 60 seconds. Now, we could calculate the number of rocks per second. It'd be some decimal, but here we can just think of it as 60 seconds because we were given 100 rocks per minute. All right, so then let's plug in our values and calculate them. Okay, so let's find the energy per rock. Okay, so that's going to be 1 multiplied by 450. Okay. Okay, plus 450, and then times 9.8 times 320. All right, so that's the potential energy. And then I just need the drag energy, so our third term. Okay, and that's just going to be 1 again, times 320. Okay, so we have about 141,000, or not, 1,411,000 joules per rock. I mean, they're big rocks and being flung to a very high height. And obviously the amount of energy that's going to drag is not that significant. It's mostly just the fact that they're being lifted up. Okay. All right. Although we do have 450 joules per rock, but still 450 is a tiny drop in the bucket of 1 million. Okay. So let's then find our value here. And it would be interesting to see, if we ignored, with the values that were given, if we ignored the internal energy change and the drag energy, that it probably wouldn't actually change the power rate that much, because, like I said, most of the energy is going to the rock's gaining potential, gravitational potential. Okay, so then we're going to use that value. So we're going to go ahead and multiply that by 100. Okay, and then divide by 60 to get our wattage of the volcano. Okay, so we get, looks like 23 million. Let's see, so 280, 300, no, so 2,352,000. Okay, so I'm going to write 2.35 times 10 to the 6 watts. Okay, so double check the number of zeros. Yep, which we could also write as 2.35 megawatts, because mega is the prefix for a million. Okay. All right. Thank you.